Let's start our substitution examples by considering the integral of the inflow example, 3 cos 2t. Many books call the substitution new variable u, but our book calls it w. Then you get the benefit of computing dw. Hey, Arthur, what should w be? It would be a bad choice to let it be t if you're really trying to use substitution in a significant way. Because if you let w equal t, you're not really doing anything different. You'd get the exact same integral. So try something slightly different. How about 2t? You're like looking at that 2t and saying, boy, I wish that was a t. By making w 2t, you're making your wish come true effectively, just with a different letter. But there's always a price to pay. Yeah, you've got to find dw. The derivative dw dt would be 2, the constant 2. But here is a convenient fiction again. Okay, I'll go ahead and write it out. Pretend that that's a fraction, even though technically it's not. Technically, this is just a symbol for the derivative. It's a limit of fractions, but it itself is not a fraction, technically. But convenient fiction, you can pretend it's a fraction and pretend that you multiply both sides by dt and write it this way. You should not write dw equals 2. That would be bad style. And maybe a point would be taken off. You should write dw equals 2 dt. If dt is an infinitesimal and 2 is an ordinary number, the product of an ordinary number and an infinitesimal has got to be infinitesimal, right? Okay, take a literal, really small positive number like 10 to the negative million power. If dt is 10 to the negative million power, which is so small, it's beyond your imagination. 2 times it is still really, really small. It's 2 times 10 to the negative million power. Yeah, not even bigger than 10 to the negative 999,999 power. Still really small, still effectively infinitesimal. If this 3 were a plain 2, then 3 dt effectively would be replaced by dw. Now it's not a 2, it's a 3. So how do I deal with that in this method? There's 2 ways. One way is you can do a little trick. Write 3 as 3/2 times 2. Make there be a 2 in there. And then once you've done that, then yeah, 2 dt will be the same as dw. But what about the 3/2? We'll just factor that out in front. And 2t itself is w. So you end up with 3/2 times the integral cosine w dw. That's one way to deal with it. An alternative way is you could solve this equation for dt by dividing both sides by 2. If dw is 2 dt, then dt is 1/2 dw. And then you can replace this dt here with 1/2 dw. And you still end up with the 3/2 coming in there again, which it has to come in if it's going to give you the same answer. 3 times 1/2. Either way you do it is okay. But do show this kind of work here. Do this integral. It's a simpler integral to do. There's the answer in terms of w, but then don't forget, go back to the original variable. Replace w by what it equals, 2t. There is the final answer. You can always check it. And when you do integration by substitution, when you check it, you will use the chain rule. Effectively, we're reversing the chain rule. Differentiate this in our minds here. But did I make a mistake? I'm sorry. Sine. Differentiate that in your mind. 3/2 stays there. The derivative of sine is cosine of 2t. times 2 because of the chain rule. 3/2 times 2 is 3. I do get 3 cosine 2t. It works. Do you have to show this work? On the homework, yes. On the quizzes in the gateway, you don't. Or just have to write answers on the quizzes in the gateway. But sometimes the examples do get kind of tricky. Here's a slightly trickier one. I mean, it looks a lot harder when you look at it. E to the square root of x over square root of x. Just a plain old w equals x is not helpful again. So what's the next thing to try? The next simplest thing to try is maybe w equals square root of x. But while we can do that, it's not clear that it's going to help. We do need to find dw. dw dx is going to be 1/2 x to the negative 1/2, but then multiply both sides by dx to get dw is 1/2 x to the negative 1/2 dx. Yes, the dx needs to be there. Is that helpful? It is when you recognize that x to the negative 1/2 is the same as 1 over square root of x. So we've almost got dw as being the combination of these two things, except for the 2. No, okay, I'll multiply both sides by 2. 2 dw will be 1 over square root of x dx. So the combination of these two things gets replaced by 2 dw. The square root of x is in the denominator here. And the w here, the square root of x here gets replaced by w. So the new integral is the integral of 2e to the w dw, which is easy. It's 2e to the w plus c. Then go back to x. 2e to the square root of x plus c. If we check this by differentiation with respect to x, the derivative of 2e to the x is itself, but it's not an x up there, it's a square root of x. So I also need to use the chain rule and multiply by the derivative of square root of x, which is this. The 2's cancel. X to the negative 1/2 can go in the bottom as a square root of x. It worked. Check. That is the same as the original integrand function that we are integrating. Next example. We'll do is this one. Should w be x? No, again, that's always a bad idea. Should it be 9 minus 4x? Maybe, or maybe just a 4x. I think 9 minus 4x will be better. Should it be square root of 9 minus 4x? I mean, after all, we did a square root there. I would try just a plain old 9 minus 4x first and see if that's good enough. Sometimes you just have to do some trial and error. Use some scratch paper. You don't have to just right away do your work on the paper you're going to turn in. Have some scratch paper, do some doodling and some scratch work, try some things. That's an important part of the problem solving process. So I'm going to try 9 minus 4x. The derivative of 9 minus 4x is negative 4. Therefore, dw is negative 4 dx. And dx would be negative 1/4 dw. So it looks like I'm going to get integral of negative 1/4 times 1 over square root of w dw. Right, the dx gets replaced by negative 1/4 dw. The 9 minus 4x in that square root gets replaced by w. And this can be done because 1 over square root of w is the same as w to the negative 1/2 power. Reverse the power rule. Negative 1/2 plus 1 is positive 1/2. Divide by the same number. That's like the n plus 1 and the dividing by n plus 1. N is negative 1/2 here. N plus 1 is positive 1/2. Dividing by 1/2 is the same as multiplying by 2. In terms of W, there's the answer, but get it back in terms of X. W is 9 minus 4x. The final answer looks to be negative 1/2 square root of 9 minus 4x plus C. If we try checking, the negative 1/2 is going to stay there. I'll bring down a 1/2 because square root is to the 1/2 power. Then I subtract 1 from the exponent. Then by the chain rule, multiply by the derivative of 9 minus 4x. Negative 1/4 times negative 4 is positive 1. And this negative 1/2 power means we can write the final answer like this. We do get the same thing as what we integrated, called the integrand function. Next couple examples are going to be such that, well, the answer is going to be complicated enough that probably guessing is close to impossible. Integrating x times square root of x plus 4 is our next example. Now, if I looked at this and thought to myself, okay, I'm going to try guessing, probably my initial guess would involve, since square rooting is raising to the 1/2 power, maybe something to the 3/2 power. Maybe x plus 4 all to the 3/2 power. Might be my initial guess. And that's fine and dandy, but it turns out to be wrong. And it turns out to be wrong enough that it's clear it's not even super close. Yeah, it does make up part of the answer, but not the entire answer. The entire answer ends up being more complicated than a superficial guess would reveal. So what do we do? Is it clear a substitution will work? No, it's not. I don't think it's clear, but you try it. And you will get a problem or two like this in section 7.1, which is the section about substitution. So that's a big hint to try substitution. Again, W equals X will not be helpful. So try the other thing, X plus 4. And cross your fingers, pray that this helps. What's dW? dW dx is 1. Therefore, dW itself is 1 times dx, or just a plain dx. So while W doesn't equal X, dW does equal dx. So the X plus 4 here gets replaced with W, and the dx gets replaced with dW. But what about that X in the front? What does that get replaced with? Kind of like the only thing you could even try is using this equation again. Solve it for X. Subtract 4 from both sides. That's like the only thing worth trying, it seems. Is it helpful? Doesn't necessarily look like it. It looks like we've got an integral that's about at the same level of difficulty. And that does happen sometimes when you do substitution, is you get a new integral that doesn't look much better. But appearances are deceiving. This actually is better. Because when we distribute the square root of W through the parentheses here, distributive property, we end up with a difference of 2 powers of W. W times square root of W is W to the 3/2, then minus 4 W to the 1/2. And now we can use linearity as well as the reverse of the power rule. You can use it with fractions, it's okay. We did that already, actually. Add 1 to the exponents. 3 halves plus 1 is 5 halves. Divide by the same number. Carry the minus sign along. Carry the 4 along. Add 1 to the exponent. Divide by the same number. Don't forget your plus c. Dividing by 5 halves is the same as multiplying by 2/5. Dividing by 2/3 or 3 halves is the same as multiplying by 2/3. Replace w with x plus 4. We get 2/5 x plus 4 to the 5 halves minus 8/3 x plus 4 to the 3 halves. So remember I told you, I would have guessed something times x plus 4 to the 3 halves at first, and I would have been wrong. It's part of the answer, but it's not the whole answer. We also have this term. Could this be written with square roots? Yeah, it could. I could also replace this with x plus 4 times square root of x plus 4. I could also replace this with x plus 4 quantity squared times square root of x plus 4. You don't have to. The square is for the x plus 4. But you don't have to do that. Checking. Checking is a little tricky in this case because when you initially differentiate, it doesn't look like it's worked. Bring down the 5 halves. 2/5 times 5 halves is 1. I'm differentiating with respect to x. 5 halves minus 1 is 3 halves. Here, bring down the 3 halves. 8/3 times 3 halves. The 3's will cancel, and 8/2 is 4. Subtract 1 from the exponent. Doesn't look like we got the right thing, does it? Doesn't look like it helped. Doesn't seem to match that. Until you do a little tricky algebra. There's a common factor of x plus 4 to the 1/2 that can be factored out. What's left here is x plus 4 to the first power. 3 halves is 1 plus 1/2. And what's left there is minus 4. Hey, those 4's cancel. 1/2 power is the same as the square root. We do get the original integrand. Check. So it works, but it's a little tricky. One more substitution problem, then I need to briefly talk about definite intervals in this context. The following kind of problem always shows up on the gateway exams. And there's different versions of the gateway exams. A product of powers of cosine and sine where at least one of the powers is odd. By the way, I did not write the gateway exams, so I didn't have a choice about this. I don't know why this was picked as a common example on every gateway. But it was not this exact same problem all the time, but a similar type. Product of powers of cosine and sine where at least one of the powers is odd, maybe both are odd. What you don't want is you don't want both powers to be even. That's a lot harder. It's a lot trickier when they're both even. If I made that 3 or 4, it'd be a lot harder. I have to use some trig identities a number of times, and it's a big pain, actually. Can be done, but it's a big pain. What you do in this context is you take the one with the odd power. Actually, in the previous class, I did the opposite. I made this a sine and not a cosine. Oh, well. Take the one with the odd power, in this case, the sine, and peel off one of those factors. Why'd I do that? Because when you do that, whatever's here, you want to be either dw or minus dw. I'll write it as plus or minus dw. That's what I want. If that's going to happen, if sine of x dx is going to be either plus dw or minus dw, I better let w be cosine. Right? If w is cosine of x, then dw, in fact, will be negative sine of x dx. This will be minus dw actually. But wait a minute, if I let w be cosine, this will be w to the fourth, but what about that? What do I do with that? I have to use a trigonometric identity to relate it to cosine. And since it's sine squared, I can use your favorite trig identity. Cos squared plus sine squared equals 1. So this is cos fourth x times sine squared gets replaced by 1 minus cos squared x. I still have the sine dx here. Let w equal cosine of x. dw then is negative sine x dx. So that means sine x dx is negative dw. And this integral becomes the integral of w to the fourth times 1 minus w squared times negative dw. You can bring the w to the fourth through the parentheses. You can also bring the negative sign through the parentheses and ultimately integrate w to the sixth minus w to the fourth. I did two things there. I multiplied the w to the fourth through and also the negative sign through, so I switched the order. So I get 1/7 w to the seventh minus 1/5 w to the fifth plus c, but that's not the final answer. I need to replace w with cosine of x. 1/7 cos to the seventh x minus 1/5 cos to the fifth x plus c. In checking this, you end up having to essentially use the same identity again and reverse your steps here. So it's checking, it's not real quick.